Hello physics students, welcome to video number 5, and in this one we're going to just recap what our understanding should be on vectors and scalar quantities. Now remember that the difference between a scalar quantity and a vector quantity is the scalar quantity will only have a magnitude, whereas a vector quantity should have a magnitude and a direction. Now we do get a little bit slack about it sometimes, like for example, we'll ask you questions where, although velocity is a vector quantity, we'll only tell you the magnitude. We'll say a car is travelling at 10 meters per second, and we treat that like a velocity. The reason being that the direction is of no consequence, because the context of the question is very specific, and so we're just looking at that little scenario. So it's a little bit confusing sometimes as to when you're supposed to give directions and when you're not supposed to give directions for velocities and things like, and forces and things like that. Generally speaking, if you are given information about direction in the question, you need to give information about direction in the answer. That's how it works. Alright. So vector addition is pretty straightforward. Most of you will probably be doing some vector stuff in your maths, or you have done it already, and adding two or more vectors together is simply a matter of combining them into a resultant vector that represents all those combined vectors. So for example, if I had two ropes attached to me and two people were pulling me at different angles, I would move in a direction that's a combination of those two forces. And theoretically, if I tied one rope around me and pulled in that direction with a certain amount of force, I could get the same movement as two people pulling on two ropes. That's how vectors work. And so let's just work on a linear one to start with, and then we'll do an angular one after that. So the first example is a boat on a river, and the boat's being rowed. Could be a motorboat, but in this case it's a rowing boat. It can move at 5 meters per second east, and it's moving in a river or a current that's also moving to the east at 1 meters per second. So you can imagine yourself rowing, and you're rowing down a big wide river that's flowing down at 1 meter per second. So you're actually going faster than that, and you would experience that. And to the observer on the bank of the river, you'd be zooming past at a combination of your rowing velocity and the velocity of the river. So your actual velocity is 6 meters per second east. Now how did we get that? Well, we used the head to tail technique, which we were introduced to in physical science. There's our information, head to tail technique. So here we have the velocity of the boat, and remembering that when we draw our vectors, generally speaking, the length of the vector is proportional to its magnitude. So here this is representing 5, this is representing 1. And we always point in the direction of the actual vector. And so here they've gone head to tail. So in this case they've drawn the boat first and then put the river on top of it, head to tail, but you could have done it in the other direction, the other order, and you would have still got the resultant, which is this length here. And they've drawn it from there to there. Okay? And that's how we add it together. Now we can do that with a variety of vectors. Doesn't have to be just two vectors. So let's consider the similar, still a linear relationship, but in this case you're rowing up the river or against the current. How does that look? Well, in this case you've got the river pointing in the opposite direction. Now I think they could have drawn it a little bit better here. Oops, let's bring that back. I would have drawn it, let's see, we're in blue, so this is your first vector, and the second vector that we're adding, head to tail, goes on top of it like that. Oh, I didn't change colour. Let's try that again. There we go. Okay, and then our resultant, let's draw that in orange, goes from here, the start, to the end of our chain of vectors, and so that would be our resultant, R. Okay, but they tried to show it a little bit there. Just the way they typeset things. Okay, and so the resultant is actually you're still moving to the east, but at a reduced velocity compared to your rowing. Okay, and I think they do the maths there, 4 meters per second east. Now here's the scenario where the vectors are not in a linear relationship but are opposed to each other or at an angle to each other. So we've got a crate. This should be sitting on a table or a floor or something, and we've got one vector pushing from left to right. It's a force vector, it's 100 newtons, and then we've got 80 newtons pushing down on it. This could be a weight force. Alternatively, this could be a top view, and we're looking down at a crate that's being pushed by 2 people, couldn't it? Yeah, can you see that? So different scenarios, same sort of problem that we deal with. All right, and so what's the crate actually going to do? Well, to calculate the resultant force, we use the head to tail technique again, and in this case they've drawn the 100 Newton force first and with the arrow, and then they've put the second force in there, and the result goes from the start of your line or your chain of arrows to the end. Now sometimes students get confused and go, well, what one should I draw first? It doesn't matter. If I had drawn the 80 Newton one first, a bit shakily, okay, that's the 80 newtons, and then I did the head to tail technique, so I put the 100 Newton ones here like this, okay, haven't drawn it exactly to scale. The resultant goes from here to here, so it looks like that, okay, and that will be FR, and it will be exactly the same magnitude as this triangle, because the relationship, you've got a right angle there, you've got a right angle there. This angle here is actually this angle here. And so it's just a flipped mirror version of the same triangle. And so the angles and everything else will be relatively the same. It's just they're mixed around a little bit. But you should get the same result. Alright. Let's get rid of that. So it doesn't matter which order you draw them in. Okay. And then you use, of course, Pythagoras to get you the length of the hypotenuse. And because it's a vector, we need the angle. In this case, they worked out the angle to be by using tan, but you could have used cos or sine because you know enough information. So you're not limited to which way you do it. All right, now addition is relatively straightforward, and we can add more than one vector together and draw a resultant. For example, if we go back, no, let's go forward, give myself a room. If I was to have someone walking along, they could go north a little bit, and then they could go east, and then they could go north, and then they could go west, and I might be asked to make the resultant of that go like that. Head to tail, same technique. Okay, so addition is relatively straightforward. Subtraction, however, is a little bit trickier when we're drawing vectors. It's okay when we're doing it mathematically, but it's a little bit trickier when we're drawing them. And the one that tricks people up a lot, especially in this physics course, is the relationship that when students are asked to resolve using vectors, either momentum or a change in velocity. And a change in momentum is a change in velocity, so they're related to each other. Now we should remember that the change in velocity, delta V, is equal to V minus U. Now we can do that mathematically if we have the numbers. However, if we're doing it in vectors where we want to resolve the directions, and which is the main reason we want to resolve it in vectors, we can't just subtract the vectors. We have to add them together. And we would recognize that V minus U is the same as writing or adding minus U. Okay. Now, if you haven't done negative numbers or adding and subtracting negative numbers for a while, that may be a little bit confusing, but it's true. Okay. We can have, let's go. 1 plus, let's delete that. 1 minus 2 obviously equals minus 1, whereas 1 plus minus 2 is still equal to minus 1. Okay, So mathematically it works. But how does it relate to vectors? Well, it's the way we draw them. So here's an example. Here we have some force vectors and we want to subtract them. So for example, something's getting pushed at 9 newtons north, and it's also, let's say it's got a friction force of 6 newtons south. Okay, we want to subtract those two vectors, and so what we do is we add the opposite to it. Okay, so it's F1 minus F2. We want to subtract those two vectors, and so we add the negative of the vector, and so they flipped it around, and you can see that the total force is now 15. Whereas if we tried to draw them head to tail, we would have got the wrong answer, which would have been 3 newtons, I think, probably. Okay, a little bit tricky. Let's have a look at a couple of examples where we would actually do this. And the key thing here is we've got a bouncing ball. It goes down at 10 meters per second and then bounces back up at 8 meters per second up. And we're asked for the change in velocity. So as soon as you hear the change in velocity and you're relating it to vectors, you've got to be careful. Okay? And so the scenario is, let's just draw it, make sure we're all clear of what we're trying to communicate. We've got our ground, there we are. Whoops, slopey ground, let's try that. That went crazy. Alright, that's better. We've got our ball, it goes down, bounces, and comes back up. And so this time it's usually at 10 meters per second, and it bounces back at 8 meters per second. Now if we say down is negative, that becomes minus, that becomes positive. Now what is the change in velocity? Now some people, if you just did vectors and did it head to tail, you would go like that, 10 and 8, and you would say, well, the resultant is that, which is 2 meters per second to the minus 1. Down. But that's not right. Okay, that's suggesting that because change in velocity delta V equals V minus U, one way of thinking about it is that the change in velocity is caused by, what causes a change in velocity? A force. And so the force that's causing the change in velocity must be in the same direction. Does that make sense? You can't have a change in velocity in a different direction to the force that's causing the change in velocity. And if we go back to this scenario here, what's causing the ball to bounce? What does it hit? What pushes it? The ground. So the ground is providing a force that causes the change in velocity. And so if that ground is pushing upwards, the change in velocity must also be upwards, which suggests, or tells us quite clearly, that this answer here is wrong. Okay? Because it doesn't conform with physics. And physics is very logical when you think about it. If you don't think about it, you'll get the wrong answers because you're not being logical. That's just the way it works. Alright, so let's look at how we would do it. And there's a variety of ways in this question. Okay, let's get my mouse back. So the first way is just to do it mathematically, which is one way of doing it. You've got enough information here to work it out. And so you say your final velocity is plus 8, initial velocity is minus 10, change in velocity is just V minus U, so plus 8 minus 10, so we're careful with our signs, minus is the same as plussing, so you end up with 18 meters per second to the minus 1 as your change in velocity. Okay? How do we do that with vectors? Because you will be asked to do this with vectors. What does it look like? Well, there's our final velocity, there's our initial velocity, 8 and 10. What we do is we flip around the initial velocity. They should have really used a U there and a U there. Okay, and this is adding the negative. Okay, so if we added these two vectors together now, we get this vector, which is our 18 upwards. And that happens to be in the direction of the force that the ground's applying. That causes the ball to bounce. And so we know that that's the right answer. This becomes important when we start doing circular motion and momentum. Okay. Let's have another look at an example. In this case, we have a change in direction. So a car's travelling 20 metres per second east, turns and accelerates to 30 metres per second north. Calculate the change in velocity. So there's our car moving, our vectors that represent it. Now, a majority of students, when they're asked this question, to calculate the change in velocity, would do their vectors using vectors. They'd put that one there, and then they can't help themselves. They draw a line from the tail of the first one to the head of the second one, and they say that that's the change in velocity. However, that's wrong. Okay? Whoops. That's wrong. Let's go back. Because, now why didn't that change over? Here we go. There we are. That's better. When you ask yourself, this car is travelling this direction, so it's sort of like a car going around a corner like this. There's our car. Okay, going like that, this way, and then it goes round the corner and ends up going that way. Alright, there's our initial velocity, there's our final velocity. There. What causes that car to go around the corner? Well, when we do circular motion, we'll see that it's a force, and there's a force, the road is providing a force in that direction to make us go round the corner. Okay, if this was the change in velocity, it would mean that the force that's causing the change in velocity is acting in that direction. Now, if you push a car this direction, or you push a car this direction, the car would change direction, but it would only change direction across to over there. It wouldn't change direction to this one, because it needs to have a component in that direction. The force does, that causes the change. So, if we were to rub out that one, and rub out that one, we can see that if this is the force, this must mean that the change in velocity is in that direction. So the force that we want is in that direction. Now, how do we draw these two vectors to give us a resultant, a change in velocity in that direction? And the way we do it is just obeying what we were saying before, which was by doing, okay, let's go back one. By using this equation here, let's go, where V equals, or delta V, delta V, change in velocity equals V minus U, which equals V plus minus U. So this is where they've changed the sign or the direction of the initial velocity. Still use head to tail, and now you get, now I wouldn't draw this vector like this, I'd put the arrow there, very naughty. Okay, you still get the change in velocity delta V in the correct direction, because that's the direction of the force that's going in that direction. Now once you get your triangle right, you could then do the maths, and the maths isn't too hard. Alright, but it's getting that triangle right that's the important bit. And so you just use Pythagoras, and then you make sure that you have an angle, and you make sure that angle has a bearing. You just don't say 33.7, you've got to give it relative to your map that you've drawn. Alright, so in the next video we're going to look at components, which is the next bit of looking at vectors. Okay, cheerio.